All right, back from break, and we have looked at 4 problems from a previous year's midterm. Let's look at another midterm. Oh, look, it's a different midterm. So from another year. So I'm looking at the diagrams here. It does look like, ooh, I got another statics problem from chapter 13. I got a fluids problem from 12, a fluids problem from 13, oscillations from 14, and now I'm getting, from 16, I'm getting a Doppler problem. I'm getting a wave problem. So that's generally how we're set up here. Let's get started with problem 1 here. We have a cable. Now it says it's a light cable. When I gave this problem, it confused students. They thought the cable was made out of light. Okay, but it's not made out of light. It's low mass. So what we decided was that, or what I intended, is that the cable has no significant mass. We don't have to include the mass of the cable. So I'm just going to say a cable is used to support a beam. Now the beam does have mass, significant amount, 80 kilograms. And then there is this, isn't that a really pretty design? You've got the beam and a sphere on the end of that. And the sphere is 200 kilograms. So, and you know, it's the usual chapter 12 problem. We're just supposed to go in and solve for everything. So let's see if we can find out all the tensions, all the forces everywhere. And that starts with a diagram. So the presence of this 200 kilogram, where are the numbers? Ooh, 200 kilograms and 80, that's a lot of kilograms. Sphere, that's going to create a force down on the beam of big mg. Now it's really a contact force, but it's going to be, the contact force is going to be as large as big mg. So we just say we're going to load the beam with, 200 kilograms times g. Now the beam itself has 80 kilograms, and we can place that at the center. It's a uniform beam. There's no reason to think it's not uniform. Now the beam is also, it's 2 meters in length. This is a little unusual. So in this problem, the cable is not connected to the end of the beam. It's connected halfway. Now that has a certain artistic effect, but it also is going to have a certain statics effect. So this is almost starting to look like, if you remember that example we did in class with the bicep lifting the forearm, it kind of reminds me of that, where this cable is not all the way out at the end. It's right in the middle in this problem. So I can take the tension in the cable and say the tension will be at the very same angle that the cable is aligned. That's how cables work. And so that's going to give me a component of t cosine theta and a component of t sine theta. That's the cable exerting a force at an angle of 40 degrees on the beam. So 2 gravitational forces, force of the cable. Now we've looked at these kind of problems before, and what we always do is we put a hinge right here, which allows the beam to kind of move. So what we're going to say here is the beam, there can be a force of the wall pushing the beam outwards, or there needs to be a force of the wall pushing the beam outwards to offset t sine theta. Now as far as Fy, the y component of the force at the hinge point, that one, initially when I started drawing the diagram, I thought, I want a force upwards to help support the beam. But then I took a look at my drawing and I said, but wait a minute, if there's a force of the beam upwards here, and all these downward forces over here, isn't that going to make the beam tip over? Anyway, I thought to offset mg, the torque from mg, needs to be offset by a force here. These lever distances are actually the same. If I'm thinking of rotations, around the center point, I would need a force Y that would balance out the mg, so that's what I went with. If it's wrong, it'll show up because when I calculate the force, I'll get a negative sign. So I know that if I now remain consistent all the way through the problem, everything's going to be fine. So, so I did this. To get the tension, I picked a point, point A, and I measured torques. So if I pick point A, Fx drops out, Fy drops out, T sine theta drops out. All I am left with is T cosine theta. Now T cosine theta has a lever distance of 1 meter, which is what I'm calling L. And then mg has a lever distance of 1 meter around point A. But big mg has a lever distance of 2 meters. So this says that T cosine theta, all the L's drop out, equals mg plus 2mg. We're used to seeing these factors show up based on lever distances. And so once again, that's what we're seeing show up in this example with the factor of 2 here. Solving for tension, it's mg plus 2mg over cosine theta. That gives me 6,140 newtons. So that is the tension in the light cable, the cable. So in the cable, there's a tension of 6,140 newtons. Now, once I get tension figured out, Fx is not difficult because Fx equals T sine theta. It's got to. They're the only horizontal components. So plugging the numbers in, it says Fx and T sine theta are 3,947 newtons. So I've got Fx calculated. Now Fy, before we were talking about if I measure torques around the center point, the only forces providing torques would be mg and Fy. I'm guessing Fy needs to equal mg based on torques, but that's actually not the way I solved it. I went ahead and used this approach. I said that T cosine theta upwards has to equal Fy, little mg, and big mg. So I took T cosine theta equals this and this and this, and then I solved for this. So Fy then would be equal to T cosine theta minus mg minus big mg. I have all the numbers, and when I solve that algebraically, I substituted in for T cosine theta. So for T cosine theta, I substituted this in, and yeah, I was able to show with the equations I'd already set up that Fy needs to equal mg. Now that's based on lever distances and the way that the cable is arranged. So yeah, Fy needs to be 1,960 newtons, same as mg. All right, questions on any of that? So again, I think that's a good problem. Maybe I would take out the word light. If I were giving this again. All right, let's take a look at the next example. The next example, okay, this is one of those problems. Don't panic if you see this on the midterm. It happens. It's an oscillatory problem, and it's got parts A, B, C, D, E, F, G. That's a lot of parts. Now, what happens on an A, B, C, D, E, F, G, H, I, J, K, elemental P problem is that often the subparts are easy, I want to say. So let's take a look before we panic. Let's see what they look like. First of all, the setup is a little tricky. So it says we have a 100 gram object suspended from a spring. And then we add 40 grams on. Now it's when we add the 40 grams that the spring stretches an additional 5 centimeters, and then the combined 140 grams is set into vertical oscillations with an amplitude of 10 centimeters. What does that look like? I have to draw all the diagrams. So here is the spring, here is the spring with the first object, 100 grams. Now that's already stretching the spring, but they didn't tell me by how much. It wasn't until we added an additional 40 grams that they told me between this picture and this picture, it stretched by 5 centimeters. Now it turns out for ideal springs that behave linearly, I can take k times x, the additional amount of the stretch, times k, will equal the additional force. And the additional force was m2g. In class, we broke this down into some smaller steps, but I'm just going to go ahead and say additional force will set up an additional stretch in the spring, and I can use that to calculate k. So I put in just m2, divided through by the 5 centimeters, converted to meters, and I got a k value for the spring that I calculated at 7.84 newtons per meter. Now, that's the k value. Now in the second part, in B, it says what's the angular frequency? Well, the angular frequency, once it goes into oscillations, will depend on both masses. So I combine those and plug those in, and I got 7.48. Now this is always confusing to me. If one of my numbers is 7.84 and one is 7.48, I don't know. I think the brain is always looking for patterns in things. That's just a coincidence. Okay, I don't think that's anything meaningful. Now this is 7.48 radians per second. Now they ask about a period, and I always think that's really good to do. So I convert it into a period, and it says each cycle is taking 0.840 seconds. In C and D, they said do some graphs. Now I know students always go, okay, if I get a graph problem, how much detail do I have to show? And I'm going to say I think drawing careful graphs is important. If you look ahead to whatever work you're going to be involved in, you need to be able to quickly sketch out a graph to show a colleague what's going on. Or maybe you're understanding something you're designing or developing or analyzing. Anyway, here is one cycle of displacement graph, and here is one cycle of velocity graph. And what you need to do is label the vertical axis. This is x as a function of t. So this axis is t, vertical direction is x. And it runs between plus amplitude and minus amplitude. That's the 0 point. This is the period. So I have the time axis labeled, the vertical displacement axis labeled. Same thing on velocity. I have the time. Oh, I don't have the time. That needs a time labeling. That's going to lose a point. So, well, probably. But it's the same time as above, and that's going to be one period. Now that's fine because I've already told people what the period looks like. And if I'm drawing graphs of oscillations, I feel like the most effective thing to do is to draw one cycle. If I draw one cycle, you know what all the cycles look like. I don't have to draw them all. I can just draw one cycle. So I drew exactly one cycle, cut it off. Below, one cycle, cut it off. And I made the times match up. So when x is at a maximum, the velocity is at 0. And then as the object here moves away from the maximum value, at least initially, the way I've done the graph, the velocity is going to go negative. So I wrote down the function for x, I wrote down the corresponding function for v. Now I could have done a sine function for x. I chose to do a cosine. I just need to make sure that the two functions I draw agree with each other. Okay, so C and D, and then, E, F, G, H, I is on the next page, I think. But anyway, take a few moments, practice drawing your graphs. Okay, so this is one important, really important, very, very important feature of labs, is making sure that you're doing your own graphing. Make sure that when you do the lab reports and when you're doing the homework problems, make sure you're always drawing diagrams, you're practicing these graphs. Because if you can't draw these graphs, it says to me you really don't understand them, and that's one of the most important skills in the course, is using graphical information to include in problem solving. Now, let's see, what's the maximum velocity, what's the maximum acceleration? The amplitude was 10 centimeters. The Vmax is omega times A. That's 74.8 centimeters per second. So that's, you know, that's a pretty good speed, maximum speed. And then the maximum acceleration is omega squared times A. That's 560 centimeters per second per second. That's 5.6 meters per second squared. That's a pretty good acceleration. And then the very last item, energy. Now, you know that the total energy can be written in terms of the amplitude, or it can be written in terms of maximum velocity. This seemed like the most direct way to solve it, so I used this approach, 1/2 kA squared. It turned out to be not so much energy, 0.0392 joules, a fraction of a joule. All right, questions on this? Again, the oscillatory problems, there's a lot of quantities that we've defined, and that means there's a lot of questions potentially that I can ask. All right, let's move on and take a look at that fluids problem. This is looking at buoyant forces, and this problem, there's kind of a story behind this problem. When I first gave this problem, this is a plastic float. It's a plastic sphere in water. There's a cable holding on to a weight. There's an iron weight attached to it. So it's kind of like a buoy. So I've got something floating in the water. It's being held in place with a weight, and the idea is how much tension is in the cable, and what's the other part? Oh, how much mass. What's the mass of the iron block needed to pull this float so that half is submerged and half is in the air? Now, when I did this, when I first gave this problem, I assumed that students would ignore buoyant effects on the iron. That didn't necessarily happen. I think half the class or so included, which makes it a much more difficult problem. So they included the mass of this, and then I had some students that went in, and we talked about this a bit in lecture, they included the buoyant effect of the air. And so I'm gonna do the full-blown solution here, but remember, well, let's just take a look and see. So here's the force diagram, which they want me to draw, and I'm going to identify 3 different buoyant effects. There's B1, B2, and B3. B1 is the buoyancy due to the air. Now I'm just going to go ahead and calculate that right now. So let's see, the buoyant effect due to half of the sphere being in the air. The sphere has a radius of 65 centimeters. It has a volume of 1.15 cubic meter. It's a pretty big sphere. So it's over a cubic meter in size. Now, half of that is in the air, and half of that is displacing air, and half of it's displacing water. So 1/2 of that volume would be 0.575 cubic meters. So the buoyant effect due to the air is density volume G. Density of the air is 1.20 kilograms per cubic meter. And putting all the numbers in, I am getting 6.76 newtons of buoyancy due to the displaced air. Okay. Now, what about the water? Well, it's the very same formula, except the volumes are the same, but the densities are very different. The water is 800 times as dense, and so the buoyant effect coming from the water is 5,635. And that's a bigger number. So this is why, in many, many practical situations, we ignore the buoyant effect of the air compared with the water. So just, for comparison, I can leave this here. Now the buoyant forces are coming from fluid pressure, as you guys know, from below and above. And you might ask, well, how can air pressure pushing exclusively downwards create a net upward effect? So the way the formulas work that we've derived, the buoyant formulas work for any shape. If the object is in two different fluids, by the time I've added the buoyant force from both of those fluids, the combined buoyant force, calculated the way we've done this here, treating both as if they're upwards, will equal the net force. If an object is surrounded by, there's a different fluid on top from below, and we integrate all the way around to find out what the net buoyant force is, this actually doesn't represent the pressure force from the air exclusively, and this doesn't represent from the water exclusively, but the combined effect due to both is given by those numbers. Okay, so what we've been calculating when we just do the water is taking the top and the bottom combined and coming up with a number that approximate that, but doesn't take into account the reduced pressure effect from the air from above. Anyway, the formulas will work with whatever shape. They're going to be fine. So these numbers are reliable. Now there's a third buoyant effect, and that's the buoyant effect on the block of iron. Now that one I can't solve for right now because it depends on, well, it's the density of water, which we know, but it's the volume of that block, and I don't know what the volume of that block is. Now I can write down a formula and say that the volume of block big M is given by the mass divided by the density of water. So what that allows me to do is I can write the third buoyant force as density of water over density of iron times big M times G. Now, I don't know what big M is. That's what we're solving for. So what I can do is I can come back to this formula and say, okay, it's B1 plus B2. I've calculated those. B3 now, I have a formula in terms of big M that we can use. Now on the other side of the equation, these three upward buoyant forces are perfectly balancing the two downward gravitational forces. We know that because we say that it's just floating. There's no acceleration taking place. The velocity is zero, but more importantly, the acceleration is zero. And so the forces balance out. And that says that when I write this formula down, I can combine the big mg term and buoyancy 3, which includes a big mg, and factor that out in terms of the densities. So again, I wasn't intending students to do all this, but they did. So now I'm gonna show how that was solved. This factor in here, I can write down the density of water. I've added in the density of iron, which was not given in the original exam. So students were coming up to me saying, "What's the density of iron?" And I kept thinking, why are they asking that? What are they using it for? They were calculating buoyant forces. So this becomes a factor of 0.873. mg is 196. When I go newtons. When I go through and calculate for mg, I find that mg is 6,238 newtons. I can take that number and divide through by the gravitational field, and it says the mass of the iron, 637 kilograms. Now you can go back and solve it, not including the buoyant effect of the air, and excluding the buoyant effect of the iron, and see how it differs. I don't think it's too different, but it could be, I'm going to say 10 or 20 kilograms. Anyway, go back and take a look and see. But this is a pretty good number that we have here now. Now in part B, they say how much tension is in the cable. And now that we've got everything else calculated, the tension in the cable is now going to be so difficult. So to calculate the tension in the cable, I could look at the block, or I could look at the float. Now I chose to look at the float. It seemed easier. The forces acting on the float are buoyancy 1, buoyancy 2. I have those numbers. mg, I have that number, and then the tension. So it says that the tension in the cable is B1 plus B2 minus mg. That's 5,446 newtons. Okay. Now mg, if you remember, was 6,238 newtons. The tension is only this much, so there's what? There's 800 newtons of buoyancy, something like that. There's like 800 newtons of buoyancy due to the iron. So 800 times 5, yeah, that's pretty significant. So maybe the answers vary by a fair amount. Anyway, that's an interesting problem to go back and look at. Okay, so problem 3, there it is. Any questions? Let me know what questions you might have. I'm going to go ahead and move on to this, I guess, the last problem, huh? So the last problem is looking at an ultrasound machine, and the ultrasound machine is being used to monitor a patient's heart movements. So the heart is beating, and putting this ultrasound up, you know, making a good mechanical connection, physical connection with the patient's chest. Then the ultrasound, which is at, what was the frequency on this? I see it down here, but I guess I never wrote it with the given. I should have it up here with the given information. The frequency they're using is the 2.5 megahertz, 2.50 million cycles per second. This is ultrasound. We are not going to hear this. But that wave, that sound, is propagating through the patient, and then it reflects on whatever boundaries we run into. So, you know, this patient's having an echocardiogram, and the sound reflects off of the heart. Now, the heart's moving back and forth, and that means that the Doppler effect that we come up with, the increase in the frequency, is it's going to vary. So the return frequency, when the heart's moving towards the ultrasound machine, the frequency will be doubly shifted higher. It's going to get shifted by the heart when it first picks up the sound, and then it's going to get sent back. So here we go. If the heart's moving this way, then F1 is bigger than F0, the starting frequency, and it reflects at F1, and F2 will be even higher. So on the first way out, F1 is equal to F0, V plus. Now here, the heart is the observer. So I'm putting the speed of the heart surface in the numerator. V is the speed of sound. Now this is inside human tissue, which is kind of like water. We're going to say the speed of sound is 1540 meters per second. The speed of the heart's not that large. So 0.20, so this is tiny, tiny, tiny compared with this. Now here, what that's going to result in is this really tiny shift in frequency coming this way. Now when the signal reflects back, we're going to start with frequency 1. This time the heart is the source. So now the speed of the heart goes in the denominator. And when we put those two effects together, it says that the return frequency is the original frequency, Doppler shifted on the way out, times Doppler shifted on the way back. That's it. That's what the formula looks like. Now remember, the VHs are tiny, tiny, tiny. The difference in frequency will be small, and the ultrasound machines, that would be, you know, really difficult to measure that slight shift in frequency. So instead, the way they're designed is there's a comparator circuit of electronics. So the ultrasound machine can compare the frequency of what it's generating with the frequency of the return signal, and it can listen for beats. So we talked about that too in class, that listening for beats, like when you're tuning instruments in band, you're looking for frequency differences. So the machine can actually look to see how much of a difference in frequency there is, and then relate that difference in frequency and calculate a velocity. So it can show a real-time image, a real-time video image of the heart moving back and forth, and it can also come up with numbers. It can calculate numbers for you, telling you what the speed of the heart surface is as a function of time. So you can watch the heart surface move forward and then move away and then come back towards and then move away, and you can get all those speeds calculated. And if you're having an echocardiogram, then they write all those numbers down and determine how healthy your heart is based on all the numbers that they've come up with. So the beat frequency will be, for the machine, is the frequency it gets back compared with the frequency that it's sent out. Now the return signal is going to be higher. How did this happen? I've got it backwards. So I did F0 minus F2. These two terms are reversed. That should be a plus sign. So again, something I should go back in the notes, and if I get back there, I'll get it changed. But something to write down right now is, usually with beat frequencies, we're not interested in whether it's plus or minus. We're mostly just looking for the amount. But specifically here, yeah, it's F2 minus F0. Let's define it. This should be reversed. This should be a plus number. I should have caught this. In any case, when the heart's moving towards, it's going to increase the frequency by 649. Now that's 649 compared with 2.5 million. So you can see it's a very slight shift, but again, by comparing frequencies, it's doable. It can be done. And then when the heart tissue is moving back the other way, those signs are going to change. So in the notes, again, I will try. There is no try. There is only do or not or do not. Let's see. So I will try and get these numbers changed, updated. If I don't, be aware that those plus and minus signs need to get changed. So the key features here, more important than the sign issue, that's kind of an annoyance, I'm going to say. Get the diagrams drawn, get the formulas set up, and conceptually think in terms of Doppler shift on the way out, Doppler shift on the way back. You have to include both of those effects are going to need to get included. Okay, I'm going to say that's it, I guess. So we've looked at 2 complete exams for midterm 3. Once again, I guess this is becoming a tradition. Laney the Eagle is here to encourage you, wish you the best of luck with your preparations for midterm 3. If there's any questions, I've got office hours, a good number of office hours out there. Stop by and let's get your questions looked at.